Hello everyone, today I'm presenting our paper called BBC Enabling BLE to Support Bluetooth Classic. I'm Hsun-Wei and my co-author is Professor Kang Shin at University of Michigan. This research was conducted at the Real-Time Computing Lab at the University of Michigan in Ann Arbor. Here is the outline of my talk. In the first section, I will first give an overview of this work and the motivation behind this research. In the next section, I will describe the system design in detail. I will talk about the high-level architecture of our system, BBC. Then I will walk through our design step by step. The steps include establishing Bluetooth Classic connection and emulating two-way communications using BLE chips, both at the bit level and at the packet level. Also, BBC need to support reliable packet delivery, and finally, BBC need to support Bluetooth Classic authentication, encryption, and transport methods. In the third section, I will present the implementation and evaluation results, and then I will conclude my presentation. I will start with an overview. Bluetooth is ubiquitous and Bluetooth devices are everywhere due to the big market momentum and huge amount of installation base. In our daily life, we can see many different kinds of Bluetooth devices, such as headphones, speakers, fitness trackers, health monitoring rings, ultra-low power sensors, and BLE beacons. According to the market research, more than 5 billion of Bluetooth devices are shipped every year, and more than 1 billion of those Bluetooth devices are audio streaming devices. However, not all Bluetooth devices are created equal. Bluetooth have two distinct protocols. The original standard is now called Bluetooth Classic. And due to more than 25 years of market momentum, Bluetooth Classic is still widely used for audio streaming for wireless headphones and speakers. On the other hand, Bluetooth Low Energy or BLE started out as a separate, distinctly different technology targeting low power applications. It later became part of Bluetooth standard and is still in active development today. In terms of industry trends, more and more Bluetooth devices rely on BLE protocol because BLE can use very extremely simple hardware with ultra-low power consumption. The market research is that single-mode BLE devices are expected to grow at the rate of 22% per year. And this is approximately 10 times the growth of other type of Bluetooth devices. Furthermore, the development of Bluetooth nowadays primarily focus on BLE, whereas Bluetooth Classic does not have any significant changes for more than 10 years. However, according to market research, most audio streaming Bluetooth devices are still rely on Bluetooth Classic. For example, the statistic is 80 to 85% of the audio streaming devices still rely on Bluetooth Classic instead of BLE. But crucially, because BLE started out as a separate radio design with a completely different hop sequences, bit processing, timing, connection establishment method, authentication, and encryption design, single-mode BLE devices are not compatible with Bluetooth Classic protocols and BLE chip cannot directly stream music using Bluetooth Classic. And existing solutions do not effectively address this incompatibility. In recent years, the Bluetooth standard body has introduced the LE audio standard to stream audio over Bluetooth Low Energy. However, LE audio is an optional feature, and even new devices can be certified without having LE audio feature. For example, Apple's wireless headphones and earbuds do not support LE audio today, even though they are certified up to Bluetooth 5.3. Furthermore, LE audio requires Bluetooth 5.2, which means that any pre-2020 device do not support LE audio. The other alternative is using Bluetooth dual-mode chips, which have both Bluetooth Classic and BLE hardware on the same chip, on the same die. However, these dual-mode chips typically involve more complex hardware and software stacks than single-mode BLE implementations. Also, as previously mentioned, the fastest growing device types in Bluetooth standard are single-mode BLE chips. And dual mode solution does not apply to devices that use single mode BLE chips. Therefore, the problem we identify in this paper is that more and more devices are adopting BLE, but many Bluetooth headphones still rely on Bluetooth Classic for high-quality music streaming. With this observation, we asked the question, can we make BLE single-mode chips directly communicate with Bluetooth Classic headphones and solve this incompatibility? The answer is yes, and we call our solution BBC, enabling BLE to support Bluetooth Classic. BBC provides two significant benefits. First, future devices can use low-power, low-cost BLE chips, while also maintaining the backward compatibility with Bluetooth Classic headphones using BBC. Second, existing BLE devices can now directly stream audio to headphones, and therefore enabling new communication paradigm and applications that were not possible before. Now I want to talk about our system design in detail, starting from the architecture. The diagram on the right shows the architecture of our system. Because BLE chips do not have the hardware processing blocks for Bluetooth Classic, the key idea of BBC is to move the entire Bluetooth Classic processing from hardware to software domain and only rely on BLE chips to transmit and receive raw FSK bits. This thin architecture offers several benefits. First, BBC has better control and diagnostic capabilities of over-the-air radio transmissions. Instead of relying on hardware to autonomously schedule and process packets, BBC has direct visibility into the radio transmission and receptions. Second, by removing the reliance on Bluetooth Classic-specific hardware blocks, we can now use simple BLE chips as the hardware. Finally, our design is highly flexible, and the lower layer processing, such as the bit processing and the packet processing, can be easily changed by just recompiling the new driver. Now I would like to present how BBC emulates Bluetooth Classic operations step by step. The first step is establishing a connection with Bluetooth Classic headphones. This is called paging in the Bluetooth Classic standard. And paging involves sending various Bluetooth packets, including ID, FHS, and POL packets. A typical paging is a random and time slot variant process that is almost autonomously handled by hardware blocks. However, because BLE chips do not have those hardware blocks to do this calculation in real time, we must design a method that emulates the paging process in software and without using the hardware. To solve this paging problem, we make a key observation. Since BBC initiates the paging process, so BBC have complete control over the bits of ID, FHS, and POL packets. And BBC also have the complete control over the frequency hopping sequences. Therefore, instead of relying on dedicated hardware to generate and process each packet in real time, BBC pre-generates valid packets and frequency hops beforehand, and then just replay this traffic and monitor the response from the headphone after the entire process. With this mechanism, BBC can successfully establish an initial connection with headphones without using dedicated Bluetooth Classic hardware. After the initial connection, BBC also needs to maintain the connection by following the time slot-based protocol in Bluetooth Classic. In addition, packets are time variant in Bluetooth Classic, and the time slot's clock value are used to seed are used as a seed to generate and process the Bluetooth bits and headers and compute the frequency hopping sequence. This poses a challenge for BBC because we want to use the hardware to maintain a very stable and precise timing, but we also can only use software to handle the computations. To solve this challenge, we designed a ping-pong mechanism. Specifically, we use a general timer on BLE chips to provide a stable time base. The BLE chip first turns on the receiver and periodically sends the current timer value along with the received payload to the driver. The driver used the timer value to process the payload, generate the frequency hopping sequences, and generate raw transmission payload based on those timer value, and send those back to the BLE chip. With this ping-pong design, we can implement Bluetooth Classic processing in the driver while also maintaining the time precision of the hardware. For the actual payload generation and processing, BBC generates Bluetooth Classic bits in the driver by adding the header and CRC, applying the bit scrambling, applying forward error correction, and adding the access code. Finally, we encapsulate these raw bits in BLE packets and send those packets to BLE chip for transmission. For receiving Bluetooth Classic packets, we reverse these operations and recover the payload. BBC also provides reliable packet delivery by running Bluetooth Classic sequence bit and ARQN bits logic in the driver. Receiving a packet with ARQN bits set indicates a successful transmission, and BBC flips the sequence bit for the next data transmission. In the opposite direction, BBC responds to a correctly received packet with an ARQN bit set packet. Additionally, the received sequence bit is also used by BBC to check for duplicated transmissions. BBC also emulates the link manager function and the authentication and encryption blocks. We implement the modified Safer Plus ciphers and the E0 encryption algorithm entirely in software. Finally, BBC's driver also handles the HCI requests and provides L2 cap support so that audio data can be transmitted using BBC. Now I would like to present the implementation and evaluation result of BBC. We use Texas Instruments CC2540 BLE chips as the hardware. This is a widely used BLE single-mode chip. Also, because this chip only supports Bluetooth 4.0, it does not even support LE audio at all. We wrote a custom driver to implement Bluetooth Classic processing and run the driver on Ubuntu 20.04. For the evaluation, we first used Teledyne Core FTS for BT, which is an industry standard Bluetooth Classic test equipment. We use this tool to test the physical layer performance, such as packet error rate and throughputs. For the system-level evaluation, we use several unmodified Bluetooth headphones and measure the performance with streaming audio with the default high-quality audio setting. The table on the right shows the various unmodified Bluetooth headphones we use in our evaluation and also their corresponding chipsets in those headphones. This is the result of packet error rate and throughputs in the physical layer. We use FTS for BT to receive 4,096 packets from BBC and count the number of correctly received packets. With long data packets such as DH3 packets, the packet error rate is roughly 3 to 5% and the throughput is about 560 kilobits per second. This physical layer throughput provides ample headroom to support A2DP audio streaming with a default A2DP default high-quality setting. For the system evaluation, we directly stream audio from BLE chip to unmodified Bluetooth headphones. Here are the results with the Sennheiser and Sony devices. The packet error rate is about 2 to 5%, and the application throughput matched the bit rate of typical high-quality A2DP audio streams. We also have the results with the Apple's AirPods result in the paper. We also measure the computational time, end-to-end audio latency, and we show that BBC can support high-quality audio codec. BBC's computation only takes about 1.6% of the packet transmission interval and is very efficient on modern hardware. The latency is within 10% compared to using off-the-shelf Bluetooth chips. And Bluetooth audio's end-to-end latency, as we can see from the table, is largely dominated by the audio codec, not by the radio operations. Finally, because BBC directly supports Bluetooth Classic with A2DP protocol, Other audio codec, high-quality audio codecs such as AAC and aptX can be directly used to provide high-quality audio experience for users. In conclusion, BBC enables BLE chips to directly communicate with Bluetooth Classic devices. We achieve this by emulating Bluetooth Classic operations in software and removing the hardware reliance. With BBC, we can add audio capability to existing and fast-growing BLE devices. Also, we enable future devices to use simple BLE chips while also maintaining the backward compatibility of Bluetooth Classic using BBC. Thanks, and I will take a question.